Anybody have any homework questions?
Number 2 will have Rankine cycle.
Okay. I think I did number 1, right?
Yeah, I did number 1, just not the other 2.
Okay. What does it say in number 4 that we don't have?
Just something like a refrigerant instead of.
Oh, yes, you can do that. Just use a different table. Just use the table for refrigerant 134A. That's the solar one?
Yeah, if we had time, I would.
Okay, let me talk about a little new stuff, and then we'll get into that. Okay, I just want to bring up enough stuff that you can do the next couple problems, and then we'll go through every one of these problems, as many as you want. We're way ahead of schedule, so. Okay.
I think I've ever heard a teacher say that.
Yeah.
Where it kind of doesn't get.
Yeah.
Usually at the end, it's like, well, we're just going to cut this stuff up.
Yeah, right. Well, there are 3 final topics in the Rankine cycle. Superheat, reheat, and incorporating irreversibilities. So first, let me talk about superheat and reheat. So we figured out before that the efficiency of this cycle is improved if you get higher temperature and higher pressure at the boiler. So the efficiency of the cycle increases for a higher temperature and pressure at the boiler. The ideal Rankine cycle, the vapor comes out of the boiler saturated, but you get better efficiency, let me get that in here. So the ideal Rankine cycle has a saturated vapor exit the boiler. But you get better efficiency if you replace the boiler with a boiler and a superheater. These two things together are called a steam generator. And the effect is a cycle that looks like this. So here's the vapor dome. In the ideal Rankine cycle, you go from this saturated vapor through the turbine. But here, you have the boiler take it to a saturated vapor. Then you heat it up further to become a superheated vapor. And this is your state 1. Then you go through the turbine. So this is the state 2. And everything else looks the same. It goes through the condenser. So this is the state 3. And then the pump. So this is the state 4. So all the way from 4 to 1 is the steam generator. This is the turbine. From 2 to 3 is the condenser, and from 3 to 4 is the pump. If you're using superheated vapor like this, every part of the calculation stays the same. The only thing that's different is now you need more than one property in order to look up values at state 1. Okay. So now you need 2 properties. At state 1 to find the entropy and the enthalpy in the table. Okay? So that's really all you need to know about superheat. The second one is reheat. And for reheat, the issue okay, so I'm going to draw not just the temperature entropy diagram, but I'm going to draw sort of a diagram of how this whole cycle works. So I'll start with the steam generator. The working fluid comes out of the steam generator and goes to the turbine, just like it did before. But we have this, now we have this 2-stage turbine. The first turbine has a high pressure, and the second turbine has a lower pressure. The working fluid goes through the high pressure turbine, and then goes back to the steam generator. where it's reheated and then sent to this second stage lower pressure turbine. And you get this total amount of work. You know, we can think of this as like, we can think of this as the work from turbine 1 plus the work from turbine 2. That's the total work that you get out of this. After that, everything looks the same. So now we go to the condenser. And then to the pump. And back to the steam generator. Okay, so why do you do this? The benefit of this, so we know that we get more efficiency out of this cycle if we have a higher pressure coming out of the steam generator. But the problem with higher pressure is higher pressure means a higher boiling temperature. And a higher boiling temperature means it's easy to get more liquid in the turbine. Okay, so the benefit is that in the high pressure first stage turbine, the boiling temperature is high. And so you can get a lot of liquid in the turbine. And that does damage, you know, it's bad for the turbine.
Like bends the tips, right?
I don't know what it does, but I mean, yeah.
It does because we have this, like the tips.
Uh-huh.
Because the heavy fluid goes outside and the tips of the turbine bend.
Uh-huh.
And then you get
right.
Here. That's
I mean, you can just imagine it's a lot more force, you know.
Yeah,
so
it
yeah.
It tends to go right on the tip because it's supposed to have such
yeah.
tolerance, and then they knurl over.
Uh-huh. That's interesting.
Yeah, I think I've seen that before.
Huh. Yeah. So what they do is instead of getting all the energy you can out of that first stage turbine, you only take a little bit of energy out of it, then heat that gas back up, get all you can out of that second stage turbine where the pressure is lower and you have less damage done to the turbine. So what does this look like in a temperature entropy diagram? So first you superheat the vapor. You go through the first stage turbine, back through the steam generator. Then through the second stage turbine. Then here is, you go through the condenser, the pump, and back to here. And I'm going to call these stages, I'm going to call this 1A. It's going into that first turbine. Then I'm going to call this 2A. then 1B as it goes back into the second stage turbine, then 2B, and then 3, 4, and back. Okay, so from 1A to 2A, that's an isentropic turbine T1. Then from 2A to 1B is an isobaric steam generator. Then from 1B to 2B, another isentropic turbine. This is T2. From 2B to 3, that's an isentropic condenser. And from 3 to 4, that is, no, that can't be isentropic, that's isobaric. Sorry, isobaric condenser. You can't have an isentropic process if there's heat transfer. Then you have an isentropic pump. And just like before, this is an incompressible material.
Yeah.
And then the last one is the steam generator. And this is isobaric. There is something that you have to, something new that you have to consider with this reheat cycle. When you think about the efficiency, you can think of that as the net rate of work done by the turbines, but we have 2 turbines now, divided by the rate of heat added at the, I'm still going to call this the boiler, but we have the boiler twice over m dot. And so now you have to think of this as W dot T1 over m dot plus W dot T2 over m dot minus the rate of work used at the pump over m dot divided by Q the first time through the steam generator plus Q dot the second time through the steam generator. And to calculate these, you'll use W dot T1 over m dot is equal to the specific enthalpy at state 1A minus the specific enthalpy at state 2A. W dot T2 over M dot is H1B minus H2B. WP dot over M dot is H4 minus H3. Q dot B1 over M dot. So this is the heat transferred to the working fluid on the first trip through the steam generator, is H1A minus H4. The rate of heat transfer the second time through the steam generator, so Q dot B2 over M dot, is equal to H1B minus H2A. Okay, so the easiest way to calculate this efficiency is just using all of these different specific enthalpies, H1A minus H2A plus the quantity H1B minus H2B. I'm just plugging in these things I just gave you. Minus H4 minus H3. Divided by the quantity H1A minus H4 plus the quantity H1B minus H2A. And just like before, because of the incompressibility of the fluid through the pump, we can represent this as V3 times P4 minus P3. Okay, are you with me on that stuff? I'm not going to do an example problem like that today, but I will next time.
You don't scroll down, you need to see that last efficiency, right?
Sure.
There you got it.
Okay. And then the last new thing is, well, we've been dealing with all these ideal cases where there's no energy loss due to irreversibilities. So how do you deal with irreversibilities? The two processes that we treat so far as isentropic are really adding entropy. So like if you think of the temperature entropy diagram, we've been treating it like this. And I'm going to call these states state 1. I'm going to call this the state 2s because that's the isentropic state 2, state 3, and this is the isentropic state 4s. Okay, but what really happens is there's entropy added during this process from 1 to 2. And since the horizontal axis is entropy, it would look something like this. And this is the real state 2. And the same thing with the real state 4. Since adding entropy to the system moves that point to the right along the horizontal axis, the real state 4 is something like this. Okay? And in order to take that into account, we're going to use this coefficient that's called the isentropic efficiency. And we'll have separate ones for the turbine. That'll be eta sub t. And for the pump, that'll be eta sub p. Eta sub t is going to be the rate of work done at the turbine divided by the rate of work done at the turbine, assuming an isentropic process. So it's like the actual over the isentropic. You can imagine that the work done in an ideal turbine is going to be higher for the same properties of this cycle. What did I say? The work done for an isentropic, an ideal one, is going to be better than the actual one, you know? And so you would expect this ratio to be less than 1. And you want it to be as close to 1 as possible, right? So we'll define this as H1 minus H2. So that's the actual difference between those enthalpies, divided by H1 minus H2 in the ideal case.
So you'll have to be given, like we couldn't.
So yeah, you can't calculate this. We'll be given that isentropic efficiency, or we'll be given something about those enthalpies. But for the most part, it'll say like, okay, 90% isentropic efficiency in the turbine. You'll use that to calculate the true H2, you know? So,
So you'll have H1 and H.
yeah, so all the calculations that you'll do, all the you'll do the same calculations that we've done in the ideal case, and then you'll basically apply this like a correction factor to give you the true enthalpy. So if you're given the isentropic efficiency for the turbine, then H2 is going to be H1 plus, all I'm doing is rearranging this definition. The isentropic efficiency times the quantity H2 for the ideal case that we already know how to calculate minus H1. Okay, so this is for the turbine. For the pump, well, the efficiency, if you have an ideal system and a system that has inefficiencies, irreversibilities, which one would you, so now we're supplying energy to the pump. So you'd expect the ideal case to require less work to be added to the pump. So our efficiency is going to switch. It's going to be like the reciprocal, you know what I mean? So for the pump, the isentropic efficiency eta sub p is going to be the work rate that you have to put into the ideal pump divided by the rate of work that you have to put into the actual pump. Just think about, so to get the ratio right, just think about in each case which one is going to be higher. And if we're talking about an efficiency, we know we're going to have something smaller than 1. And then that'll help you get the right numerator and the right denominator for both of these. Okay? Are you with me on that? The turbine, we're getting energy out. So the bigger thing is going to be the ideal case. So that's in the denominator. Okay? For the pump, we have to put energy in. So the actual case is going to be the bigger amount of work. And so that goes in the denominator here. Okay. I mean, I'm going to give you all these equations, but that's just kind of a way to make sense out of it. And we can define this as H4S minus H3 divided by H4 minus H3. We have something else going on with the pump. Remember, a lot of times we use the fact that this working fluid is incompressible for the pump. So we can also write this as V3 times the quantity pressure for 4S minus the pressure at 3 divided by V3 times the pressure at the actual 4 minus the pressure at 3. These cancel. And so you get pressure 4S minus pressure 3 divided by pressure 4 minus pressure 3. So what that says is if you know the isentropic efficiency for the pump. Then H4, the actual H4, you can calculate as 1 over that isentropic efficiency times H4S minus H3 plus H3. And you can also use that the pressure, the actual pressure at state 4, is 1 over that efficiency times the quantity P4S minus P3 plus P3. Remember, you'll still calculate H2S and H4S the same way you did before. You know, when I say before, I mean like for the ideal cycle. So I think the way to think about this is just like a correction factor. You're going to do these calculations for the ideal case, but then you're given this extra information. We know we lose this much energy due to inefficiencies. So then you apply this correction factor that lets you come up with the true values of those enthalpies or pressures. And then you can use that to calculate efficiencies and whatever. Go back and calculate all the stuff you did before. Okay. Let's see. So number 2, you would like to see. Let's see how far we can get in number 2. And I'll go into some examples with this new stuff next time. So it's water. This uses superheat.
Yep.
You have some pressures. So basically, like always, we're just trying to figure out the enthalpies at those different states. We know it's water, so we have a table.
I actually just like to know how that. The enthalpy at 480 is 3,026.93, and the entropy is 10.29703.
Those are what you calculated?
Yeah, because it was,
Oh.
it was the exact midpoint number is 470, and this was 480, so
Mhm.
there had to be some interpretation done.
Okay. Water vapor, saturated. Okay, so those should be all the tables we need. Okay, so Rankine cycle number 2. We know that it's going to look like this. Where this is 1, 2, 3, and 4. It's an ideal Rankine cycle, so we're not going to use that, the isentropic efficiency. And we'll just start filling out what we know at these different states. So state 1, state 2, state 3, state 4. From 1 to 2, we have this isentropic turbine. 2 to 3, we have an isobaric condenser. Then an isentropic pump. And then from 4 to 1, we have an isobaric steam generator. This water enters the turbine at a pressure P1 of 10 megapascals.
Equal to 100 bar.
Yep. And a temperature of 480 Celsius. And so we have enough to look stuff up in the table. We needed the 2 different properties, but we have them. The condenser pressure, let's see, condenser pressure is 6 kilopascals. So we know that P2 is 6 kPa, and since that's an isobaric process, we also know that P3 is 6 kilopascals. Both of these are saturated, so we have enough information to look stuff up in the table here. State 2, though, is a mixture of liquid and vapor, so we're going to have to find the quality for that. Okay, so I guess the first thing we want to do, since we know that 1 and 2 have the same entropy, is use the table to look up the specific entropy at state 1.
6.528.
Times 10 to the third, right? And that tells us that also S2 is 6.5282 times 10 to the third. And so now we can use what we know about state 2 to figure out the quality. So 6.5282, I'll drop the times 10 to the third.
Did you get that regular, whatever your table is? When I looked at mine.
480 and 10. Uh, 30 bar, 100 bar, 480. Yeah, so there it is. And then, so this is equal to the quality times, oh shoot, I took the wrong saturation table. I need the saturation table that's based on pressure. Dang it. You don't have that in front of you, do you?
I know the values.
Okay.
State 2,
So do you have the one for the saturated vapor? The
yeah, saturated vapor would be 8.3304.
okay.
And then the liquid is 0.5210.
0.5210. And so from that you can calculate the quality. And do you have the quality?
0.769.
Okay. So now that you have the quality, you can say that the enthalpy at state 2 is equal to 0.769 times 2567.4 plus 1 minus this, which is 0.231 times, what is it for the liquid?
151.53.
And then what do you get for that?
2603.12.
25
260.
260.
3.12.
Okay, and that's times 10 to the third. Okay, so we're sort of, just on our way working through it now. Yeah, if you want to keep going on this next class, or is that enough?
Yeah,
For-
I feel like there's something relating to, me not having a lot of experience with questions that don't include the mass flow rate and or the amount of work generated by the turbine.
Okay, yeah.
I feel like that's a whole
Okay, well, just remember that basically every question that they ask can be answered if you find those specific enthalpies at those states. So that's always just your first job, is just trying to find those specific enthalpies. But I can finish that next time. Okay, that's all. Goodbye.